For those who don't know what transfinite numbers are, the transfinite numbers, the first one is called Aleph null, the second Aleph 1, the third Aleph 2, and so on. And first of all, it's most interesting to know what is meant by Aleph 1. Now, you have to imagine somebody bringing you a list of numbers of irrational fractions, that is, the non-terminating, non-repeating decimals. And they tell you that this is an infinite list and that every irrational fraction is in the list. Now, it's known that every irrational fraction could not be in this list. And the proof of it is one of the simplest proofs in all mathematics. It goes like this. Let's say that the numbers, the irrational numbers are, of course, non-terminating decimals, and they're described across the page like this. And they are counted 1, 2, 3, 4, 5, 6, 7, 8, and so forth to infinity. And as I say, the claim is that... who was that? Did you hear that?
Yeah.
I have to stop it here. Square root of 2 would do.
Yeah.
That would be a non-terminating, non-repeating decimal.
Yeah.
It would be an irrational number. It wouldn't be on in the same category as pi, by the way, but they don't need to know all that right away. Pi is not only irrational, but it cannot be expressed in terms of radicals. You know, like 3 times the square root of 2 times so many times the square root of 3, or something like that, you know.
Right.
That would be what they call a transcendental number, because it would be excuse me, I said it wrong. It would be an irrational number, but if it cannot be expressed in terms of radicals, which would be like your square roots, cube roots, and all kinds of combinations like that, you know. If the number cannot be expressed in that way, then it's called a transcendental number. It is not only and it not only has an infinite number of digits which never repeat, but it also cannot be expressed by means of radicals, using square roots of, or not necessarily square roots, but any kind of roots of numbers, you know, combined in various ways and so forth.
And pi is one example. Another example is Euler's number.
That could be. I don't know about that in particular. It's true of E.
That's what I mean. E.
Yeah.
Euler's number E.
Well, yeah, but that's not Euler's. That's not Euler's constant. There's an Euler's constant. It's true that they sometimes associate E with Euler, and also they associate it with exponential, with the word exponential. But there's also an Euler's constant, which is an entirely different thing. I've got a few hundred digits of it in somewhere here, but it tells that no one has determined whether it is irrational only or whether it is transcendental. They don't even know whether it might not be a rational number. That is, they don't know whether, if it's calculated far enough, they might find that that suddenly comes out even.
Mm-hmm.
So, so don't take Euler's number as an example, but but the E is number referred to as E is the I'm having trouble with my mind, as you can see, is let me see, what is it that I'm trying to say here? The number E is an example of an irrational number which cannot be expressed by means of radicals. I think I was saying that before.
Mm-hmm. Right.
All right. Now let's say that someone brings you a list of non-repeating decimal fractions, and he has them counted. Well, I'm just going to draw a line for each of these. There's a. Does that show on there? Yeah. All right. These lines are intended to go on forever, and they're lines of digits with the decimal points like right there. And we'll draw a few of them here and count them. 1, 2, 3, 4, 5, 6. I think I've already got the numbers down that far. Okay. Now, somebody brings, let's say you bring this list to Merla, your wife here. She's going to win this argument, by the way. And you say to her, this is a list, an infinite list of irrational fractions. They go on for, each one goes on forever, and they never repeat. And that's what makes them irrational, and there's an infinity of them, and they are all in this infinite list. And you, Mike, are saying this to Merla. And Merla says, no, they can't all be in there, and I'll prove it. Mm-hmm. And she does it like this. She says, I'll construct a number that isn't in this list. I'll give a rule for the constructing of it. And since this rule can be applied in infinitely many ways, it will prove that there's an infinite number of rational or irrational fractions that are not in your infinite list. So how does Merla do it? She says, let's say that that we write down a few of the initial digits of each one of these numbers. 1, 2, 0. Golly, this pen isn't working very well. 8, 5, 7. That's good enough. Now, I'm going to ignore these digits here and separate these a little bit.